To capture the massive scale of the modern energy transition, we have to look at what happens when variable renewable power needs to be converted into a continuous industrial commodity. Wind and solar generation are entirely intermittent. They do not naturally align with the continuous energy demands of heavy transport, steelmaking, and chemical processing, sectors that resist direct electrification. To bridge that gap, power grids are turning to the electrolyzer. This is a multi-megawatt, highly controllable electrical load designed to absorb fluctuating power. This map tracks over 680 global hydrogen projects, showing the distribution of planned electrolyzer gigafactories with capacities exceeding 0.2 gigawatts. This is the power to hydrogen pathway. It allows operators to take surplus clean electricity and convert it directly into a storable energy carrier. The chemistry relies on a simple equation. Water molecules are split into pure hydrogen and oxygen gases, a process driven entirely by direct current electricity. To understand how this works at a utility scale, we have to look inside the electrochemical core and compare the two dominant architectures, alkaline and proton exchange membrane. The engineering decisions made at the microscopic level inside these cells dictate exactly how these immense facilities interact with the larger power grid. Applying a direct current across a water molecule forces a non-spontaneous redox reaction. Energy is actively pushed into the system to break the chemical bonds. This happens inside a basic electrolysis cell, which consists of three distinct components: an anode, a cathode, and an electrolyte separating them. At the anode, an oxidation process occurs. Water molecules are broken down, releasing oxygen gas, along with protons and electrons. Those electrons travel through an external circuit over to the cathode. Here, a reduction process takes place as the electrons combine with the protons to yield pure hydrogen gas. This IV polarization curve plots required voltage against drawn current. The reaction begins at the reversible voltage, the thermodynamic minimum. Power demand then spikes along the activation overvoltage curve. Finally, the linear ohmic overvoltage slope represents energy lost forcing ions through the electrolyte. A single cell produces a fractional amount of gas. To achieve megawatt scale output, hundreds of these individual cells must be stacked in series. Maintaining that stack requires a massive surrounding infrastructure known as the balance of plant. This includes gravimetric water separators to isolate the gas streams, and pressure swing adsorption units to strip moisture from the raw hydrogen. Feeding electricity to the stack requires a dedicated power conversion system, utilizing immense AC to DC rectifiers that pull power from the transmission lines. An electrolyzer plant's true efficiency is determined by how well it overcomes internal cell resistances while powering that massive, energy-intensive balance of plant. The most commercially established architecture is the alkaline electrolyzer. Operating at a technology readiness level of 9, it serves as the industry baseline. Inside an alkaline cell, the electrolyte is a liquid, typically an aqueous solution of potassium hydroxide, separated by a porous diaphragm. The ion transport mechanism relies on hydroxide anions carrying a negative charge through that liquid solution toward the anode. Because the environment is highly alkaline, manufacturers can construct the electrodes using cheap, abundant catalyst materials like nickel and iron steel, keeping capital expenditures low. That cost advantage comes with a strict engineering bottleneck. Alkaline cells operate at very low current densities, restricted between 0.2 and 0.4 amps.
To compensate for the low reaction density, utility-scale alkaline plants require a sprawling physical footprint to hit their target capacities. They also lack operational agility. Alkaline plants have a highly restricted turndown ratio, meaning they cannot easily match a drop in wind or solar generation. Dropping load below 20% capacity triggers gas crossover. At low loads, oxygen production at the anode slows, causing a sudden pressure drop. This imbalance physically pushes hydrogen molecules backward through the porous diaphragm, directly into the oxygen chamber. This crossover ruins the purity of the product gases and creates a highly explosive mixture inside the plant's plumbing. To prevent this hazard, operators must continually supply a standby voltage to maintain pressure, drawing power from the grid even when renewable generation stops.
Alkaline technology provides cost-effective hydrogen production for stable baseloads,
but it struggles to safely absorb the erratic generation of variable renewable power. To handle dynamic, rapidly fluctuating grids, engineers utilize a different architecture entirely, the proton exchange membrane, or PEM. PEM cells discard the liquid potassium hydroxide. They rely on a solid perfluorosulfonicated ionomer membrane in a highly compact zero-gap design. Instead of moving negatively charged hydroxide ions, the PEM structure shoots positively charged protons directly through the solid membrane to the cathode. This efficient transport yields high current densities between 0.6 and 2.0 amps per square centimeter, allowing the entire stack to be physically much smaller. More importantly, a PEM plant can safely ramp its power draw from 0 to 100% load in a matter of seconds. That capability directly solves the curtailment problem of variable renewable energy sources. The PEM system acts as a grid shock absorber. Its power consumption perfectly tracks erratic generation spikes without any risk of gas crossover at lower load levels. This performance requires a severe material trade-off. The solid fluorinated membrane creates a highly acidic operating environment inside the cell. To survive that acidity, the electrodes must be constructed using expensive noble metals, specifically iridium or ruthenium at the anode and platinum at the cathode. PEM architecture delivers the agility required to safely integrate volatile renewable power, forcing developers to absorb substantially higher material capital expenditures up front. Moving away from the microscale cell chemistry, these technologies present a secondary set of challenges for the high-voltage transmission lines. Grid operators require both profiles: massive alkaline installations to process large baseloads, and agile PEM arrays to provide rapid frequency regulation. Interfacing either technology with the grid requires massive AC to DC power electronics, utilizing large banks of thyristor or IGBT-based rectifiers. These rectifiers function as immense, highly nonlinear loads on the electrical network. They do not draw power in a smooth, continuous wave, which means they inject severe harmonic distortions back into the power system. The rectifier disrupts the incoming waveform, sending a jagged, distorted signal back upstream toward other grid assets. If left unmanaged, these harmonics cause overheating in transformers, trigger equipment malfunctions in neighboring wind farms, and violate strict grid code compliance. Connecting these multi-megawatt plants requires developers to implement complex harmonic impedance models and specialized filter designs directly at the 220 kilovolt point of connection. Scaling up green hydrogen production relies on mastering the microscopic electrochemistry of the water molecule, while simultaneously engineering solutions for the macroelectrical physics of the transmission grid.